Hi guys, in 2-6 I'm going to deviate a lot from the way that the book tries to explain family of functions and just kind of go my own way with it, try to make some more sense than I have hopefully in the past. We're going to keep the same vocab just so we understand what a parent function is. A parent function is the simplest form in a set of functions. Try to keep my left hand out of the way. That form a family. That probably doesn't mean a lot to you, but like all y equals mx plus b, those are all families of a linear function. So as long as they take the form y equals mx plus b, that means they're a type of a family of a function. We're going to have today, we're really going to focus on these transformations. Transformation is a function that's different from the original or the parent function. Now, there are different types of transformations. There are translations. Translations are a move or a shift. Move/shift of the graph up, down, left, or right with no other changes. The other type of transformation is a reflection. And a reflection is a flip of a graph of a function around one or both of the axes. So it's like upside down or it's been rotated left and right. Another type of transformation is a vertical stretch. A vertical stretch is going to multiply all the y values of a function by the same factor. And in order to get bigger, in order to stretch, it has to be greater than 1. Greater than 1 means it's stretching, and then on the flip side, the last type of transformation we're going to talk about today is a vertical compression. It's going to do the same thing. It's going to multiply an equation, or all the y values, so all the vertical values, by the same factor. But this time, it's going to be between 0 and 1. For example, 0.5 or 3/4. Okay, you'll see that out in front. Let's go ahead and take about what these could all look like. So the different possible transformations. This is going to say transformations. Okay, the first kind are translations. We could move a graph up, which is a very easy thing to see. We could move a graph down. That's another easy thing to see. We could move a graph right. This one's a little harder to see. And left. This one's also just a little bit harder to see. If you're going to move a graph up, it's going to have your original equation called f of x, and we're going to add a value to the back of it. So I'll just write add a number. If we're going to move a graph down, you're going to have your original function or original equation minus a number in the back. If we're going to move an equation right, it's opposite of what you think. You're going to have your original function, but with the x values, you are going to subtract a number from your x values. I'll show you what this looks like with real-life examples. If you move something to the left, you're going to take your x values, and believe it or not, you add a number. That's hard for kids. They think right is adding and left is subtracting, but it's opposite of what you think. Let's talk about reflections. If you are going to reflect something around so I'll write around the x-axis, you are going to multiply the equation by -1. The entire equation by -1. If, on the other hand, we don't see this too much, if we're going to flip it around the y-axis, you only multiply the x value by -1. This one's hard to see, but I mean I can show it to you, but that one's kind of hard to see. Stretching and compressing. Let's talk about a stretch first, and let's write vertical stretch. We can abbreviate that later. It's just like a V and an S for vertical stretch. What you're going to do is you're going to have your original function, but it's going to be multiplied by a number in the front, and that number has to be bigger than 1. So I guess I could write maybe like an example like 3 f of x. You just have to multiply everything in your function by 3. And then you could have a vertical compression. So you'd have your original function f of x, but all those values would be really short, like maybe 1/3. All right, let's see this in play for a couple of examples, because right now it's just a lot of definitions. First one, linear. All linear equations are y equals mx plus b. Some form of y equals mx plus b. You graph it using your knowledge of y equals mx plus b. Let's pretend that we have a random parent function, very, very, very basic. Y equals, let's just do y equals, let's make it really basic. Y equals x. That's a parent function. It is linear. It has a y-intercept of 0 and a slope of 1/1. So what I want to do now is play around with this equation and move it. Let's move this equation down 2 units. All right, that's just going to be y equals x minus 2. Because you just throw a minus 2 in the back. See how, that's what I was trying to get at over here, is that if you're going to move something down, you just do minus a number in the back. Okay, now let's move it up. That's just going to be like y equals x plus a number, so like plus 5. So we moved it up 5. Now let's practice vertically stretching it. Okay, we could, as long as we multiply x by a number, so we had, remember how we had y equals x? Well, if we vertically stretch it, how about we multiply it by y equals 6x? That's a vertical stretch of 6. Let's do one other thing. Let's move it, let's reflect it and move it. So let's go ahead and reflect it, and let's move it up 4 units. Oh, I don't know why I wrote reflect. That's what I wanted it to be. Oh my, that was really bad, guys. Sorry. We're going to reflect it and move it up 4 units. So we had our original. Remember how we had y equals x? Well, to reflect it, we multiply it by a negative. That reflected it. And to move it up 4 units, we do a plus 4 in the back. Let's play around with a different function. Let's say we had the linear function y equals 3x minus 2. It's a linear y equals mx plus b. You would know how to graph that. Let's move this equation. Let's move it up 10 units. So we're going to have y equals 3x. Now, in order to move negative 2 up 10 units, we add 10 to it. So it's like negative 2 plus 10 is now a positive 8. That moved it up 10 units. We haven't moved it left or right now, so let's do that. Let's move it to the right 5 units. So we have our original, y equals 3x minus 2. To move it to the right, with x, take a look, I'm keeping the 3, I'm keeping the minus 2. But to move it to the right, if we flip back to the front, to move it to the right, I need to do x minus a number in parentheses. So something like this would move it to the right. X minus 10. Oh, well, I said 5, didn't I? My bad. X minus 5. I apologize. Move it to the right 5. That moved it to the right 5. So that kind of gives you an idea how to move things up and down for right now. Let's do one more. Let's vertically compress it by 1/3. This can get a little hairy sometimes for people. So instead of having y equals 3x minus 2, now we're going to have y equals 1x minus 2. Now, notice the 1, it used to be a 3, right? The reason I did that is because it was 3x, right? And that was the slope. So to vertically compress it, I had to multiply by 1/3, which is where I got that new 1x. Let's talk about quadratics. Quadratics tend to take the most basic thing you need to understand is that quadratics have an x squared. Now, there's a lot more about quadratics we could talk about, but right now let's just understand quadratics have an x squared. You don't know how to graph these, but we should maybe from Algebra 1, but we haven't talked about it yet. You do graph it using an XY chart like that. And typically, guys, if you remember from Algebra 1, you pick these x's. That was just kind of like a basic thing we would pick to make sure it's a nice picture. There's a little bit of a rule I need to tell you, though, that will apply in Chapter 4. Now, right now, you will change your x values if you're moving left or right. L and R, left and right. But we can talk about that more later, okay? Let's say we have that parent function of y equals, well, let's make it 4x squared. That is quadratic because it has a squared. Now what I want to do is I want to play around and I want to move it a little bit. Let's move it two ways. Let's move it up 5 units, and let's move it left 2 units. Ready? So we're going to have y equals, we're going to keep our 4. Now, here's where we're going to be really careful. Moving it up 5 units puts a big plus 5 in the back of our equation. To move it left 2 units, you need to have some parentheses with your x, and you do x. Now, if you flip back to the front, I said to move something to the left means you add a number to x. So if I want to move this equation to the left 2 units, I will do plus 2 to the quantity squared. And that moved my graph up 5 and left 2. Now let's go ahead and instead let's make a new equation. Let's vertically stretch it by a factor of 3. All that means is that you have to multiply by 3. So your new equation will be 4 times 3 is 12x squared. Because 4 times 3 is 12. Let's go ahead and reflect it around the, let's reflect it, I'm going to spell it right this time, around the x-axis. And let's move it 3 units right. Ready? So to reflect it around the x-axis, we do y equals, we just have to make it negative, so negative 4x squared. And to move it 3 units right, I need to erase that squared. To move it to the right, x needs to be in parentheses, and we need to have a minus 3 with our squared. So this negative sign reflects it, and this minus 3 inside moves it to the right. We could do another example, but I think we're going to have plenty as we move on. An absolute value graph pretty much takes the form of y equals absolute value of x like that. Again, you would graph it using an XY chart. And from Algebra 1, hopefully you remember, those are typically the x's you pick. You will change the x values, by the way, if you're moving left or right. We'll talk a lot more about that when the time comes. Let's say we have the parent function y equals absolute value of x minus 2. And I ask you to move it to the left 5 units. You would write y equals, moving something to the left means you change the x value inside. So I'm going to do x. Now remember, left is opposite of what you think. You think left might be minus 5, but it's actually plus 5. That moves it to the left, minus 2 in the back. If I wanted to move this one down 3 and right 5, let's practice what that would look like. Okay, so in order to move down 3 and right 5, we write y equals. To move it down 3, I have to take 3 away from this back number. So when I take 3 away from this back number, I get a negative 5 because negative 2 minus 3 is negative 5. When I move right 5, that goes in absolute values with x, and it would be x minus 5. It's opposite of what you might naturally want to say. So right means minus, and down means minus from the original. We could do another one, but I think you're hopefully starting to see the concept here. The last one to make sure is I tell you what cubic would be like if you had y equals any type of x cubed. Again, you would graph it using an xy chart. You might not remember this from Algebra 1, but we'll go over what x's to pick. We'll go over this in a later chapter, okay? Cubics come up again in Chapter 6. And yeah, you would change the values if you're moving left or right, but again, we'll talk about the x's that you need to pick in Chapter 6. The main idea right now is that you can like translate something. So if you have y equals x plus 2 quantity cubed, this is a cubic function. I want to practice two things. Let's move it left 3 and let's move it up 10. The easy part is the up 10, I think. So you're going to have your y equals, you're going to have your original set of parentheses cubed. You're going to have something going on with x. Now to go up 10, you just put a big plus 10 on the back because there was nothing before. Essentially, there was a 0. To go left 3, I have to take this number. Now remember, left actually means adding, believe it or not. So to go left 3, I have to add 3 to this positive 2. So that would move it left 3 and up 10. Let's practice reflecting it. And let's practice